Hello, my name is Julio Carrasquel. This is a tutorial for the double degree bachelor's program in Data Science and Business Analytics of the Higher School of Economics in Moscow and the London School of Economics. We have organized this short tutorial in two parts. First, in this video, we are going to introduce what are graphs, to give some real-life examples about their uses, how they can be represented in computers, and finally, we are going to talk about algorithms to move through them, how we can search elements in graphs. Then in the second video, we are going to carry out a bit more practical demonstration, showing a couple of programming exercises with graphs in C++. What are graphs? Graphs are mathematical structures. They consist of nodes, so graphically they are the circles, also called vertices. In the image, you see a graph with 4 nodes, A, B, C, and D. Abstractly, these nodes can represent people, places, and any class of object. Also, there are arcs depicted as lines. So they are also called edges. So edges connect pair of nodes. So this can be useful to know who is friend of who, some direct connection between cities, etc. This is why we say that graphs allow to represent relationships between objects. There are undirected graphs, where edges, so you see in the image, they don't have direction. So this means that in the line, the edge, there is no a final arrow pointing to some node. We will see another variant soon. So for example, in this graph, here we can move from A to C, but also we can move from C to A. So there is no restriction in the direction. Instead, for these other kind of graphs, directed graphs, you can see that all edges have an unidirectional sense. So for example, for the case of nodes, again, between A and C, now we can move just from C to A and not in both directions as before. Graphs also can be weighted. So in this case, edges, they have some values. For example, if nodes are towns, we may say this could represent that the values in the arcs are the cost of bus tickets. Graphs are used to analyze all kinds of subjects. For example, this is the graph of the internet for the year 1999. Of course, now it should be even bigger. Here the nodes, they represent the sites. This is another example of a global migration graph where each country can be seen as a node. And the edges, they represent the movement of people from one country to another. Here the idea is that the thicker or the bigger the edge is, it represents a greater movement of people from one place to other. Actually, without noticing, all of us used to resolve problems based on graphs. For example, in the metro, when we want to move from station A to station B, we look for the shortest route, for the one with minimum number of stations. Actually, we use even to take care of other variables. For example, we may not like a route if we have to make line transfers. Other common problem when traveling. Suppose we want to travel by train from Moscow to any other favorite city in Russia. So how many cities in such route we could visit? Or which could be the cheapest route from Moscow to any other destination that we have set? Here instead, this is a classical problem of graph theory from Euler. In the city of Königsberg in Kaliningrad, there are 7 bridges, as you see in the image. So the problem is as follows. Is there a path through the city in which we are going to visit, in which we visit all of the bridges exactly once? So this problem can be formulated as a graph thinking like follows. So where the bridges are represented by edges and the mainlands or the parts of the city are represented by the nodes. So in the graph, the question would be, is there a path through the graph in which each edge, so this means each bridge, will be visited exactly once and visiting all of these edges? This is other problem instead with bipartite graphs, with graphs that are divided into set of nodes. And the idea here is that we want to match each node from a set to another one. So here we want to assign each man to a woman according to his or her preferences. I will not discuss in detail each of these problems, so the main message that I want to transmit you here is how with graphs we can solve all these kind of routing problems when checking routes or assignment problems when checking assignments between classes of nodes. Here, for example, instead of having men and women, we could have had jobs and employees. So the problem would be try to look for an assignment between employees to jobs in the most optimal way. And all these problems can be solved using graphs. Of course, for resolving all these problems, we need to first understand how we can represent graphs in the computers. So in this part, we will talk about two classical representations. The first one is with adjacency matrices. So here we consider a matrix of dimension according to the number of nodes. In this graph, we see 4 nodes. So the matrix here is 4 per 4, 4 rows and 4 columns. Each position of the matrix says where there exists an edge connecting 2 nodes. For example, between nodes 2 and 1, there is a value 1 in the matrix in position row 2 and column 1 because the edge indeed exists. There is an edge connecting both nodes, 2 and 1. For nodes 4 and 1, you see that the value in the matrix is 0 in position row 4 and column 1. The value is 0 because there is no edge connecting such nodes, 4 and 1. Notice also that this representation is useful for direct graphs. So in the case of direct graphs, the index of the row tells us the source node, and the index of the column tells us the destination node. So here you see that, for example, row 3 and column 1 is saying that there exists an edge connecting from node 3 to node 1. So which is the advantage of adjacency matrices? So the access. So it's fast to access, so it's constant complexity, the access. You just need to ask for the position in the matrix. Instead, the minus, the thing that is not so good is the memory complexity. So if the graph turns to be very big, the size of the matrix can increase. So there are problems in memory efficiency here. The second variant of representation is with adjacency lists. So here we have a vector of dimension according to the number of nodes. Each vector position, each vector index I, will be a list indicating the neighbors of a node. For example, for the node 2 in this graph, there is a list with elements 3 and then with 4. And you see that these are the 2 neighbors of the node number 2. So you see here that it's more efficient in terms of memory, but now the access is not in constant time. So it was not as fast, it's not as fast as with the matrix. So you need to make a pass through the list of nodes. So and this list will be as big as the number of neighbors of a node. We will visit again this topic of representations of graphs in this tutorial. So in the second video, I prepared an exercise for representing a graph in C++. For now, in the rest of this video, I wanted to continue with about search algorithms in graphs. So how we can move properly through graphs and how we can visit nodes. So we will talk about 2 algorithms. So the first algorithm is called DFS. So here the principle is that we would like to explore as deep as possible. So starting from a first node, for example, node 1, we will try to move as deep as possible into a path as long as it can be possible before moving backwards. So we start here with node 1, so we mark it as visited. So you see here that we put some location icon. When being in node 1, we are going to check its list of neighbors. So here which are the neighbors of 1, 2, and 5. And we are going to select an unvisited one. So both nodes 2 and 5, we haven't been there. So we are going to select one of them. For instance, let us select the node 2. So you see that I mark it as visited the node 1, so I put it on the list. We move it also to node 2, and I am also marking it on the list of visited nodes. So here we have also 2 options. Sorry, we have 3 options. We have either node 4, node 6, and node 3. So again, the idea is to select one of these options that have not been explored. None of these options have been explored, 6, 4, or 3. So we can move to one of them. So suppose we move to 3. So now we have updated our list of visited nodes. So now the visited nodes are 1, 2, and 3. And we repeat the procedure. So now in 3 we can move either to 4 and to 7. So let us suppose that we move to 7. So you see how we have been constructed our way. So starting from node 1, 2, 3, and now 7 is the last visited node. So here we have options. As options we have 3, 6, and 4. You see that 3 we already visited, so we are not going back now. We have nodes 4 and 6, so let us suppose that we keep moving to 6. So what happens now in 6 here? So in 6, which are the neighbors of 6? 2 and 7. But we just came from 7, and 2 was already visited before in our path. So what we are going to do now is that we are moving to step back. And so we are going to move to step back, and we are going to consider the other options. So again, you saw that 6 we just visited, we just came from it. We also came from 3 in the route. So the only option available here is to visit 4, the node 4. So that's what we do. So now we go through other branch. So we move to node 4, we mark it as visited, and then we return again in our route. So you see that almost all of the nodes have been visited. So then we have to move backwards. Because here in node 7 there is no any other option left of an unvisited node. The same case when we go back to node 3. So you saw that node 4 is already visited, node 7 is visited, and also node 2. So we need to go back in our algorithm to node 2. The same in node 2. So all the nodes, all the neighbors of node 2 have been visited. So you see at the end that what we need to do is to go back to the starting node, to node 1, and to go for the node that has not been visited, which is node 5. So we move back to node 1, and then we will be able to go to other branch, to the other branch that we have not visited, the node number 5. And in this way we have now all nodes visited. So you saw in this example how with DFS, deep first search, and that's the reason why it's called, because we go as deep as we can into a branch before returning to another, before moving back and trying with other branch. You see now that we have visited all of the nodes. The second algorithm, it's called Breadth-Firsth Search. So here the idea, in contrast with DFS, is that we are not going to move as deep as we can, but as broadly as we can. So we are going to first visit all the neighbors in one level before going deeper into a path. So for example, here, starting from the starting node, node 1, we are going to visit first 2 and 5. So you saw that in DFS, we need to visit all the deeper branch of after 2, all the neighbors of 2 before moving back and to visit 5. In this case, it's different. So in this case, we are going to visit all neighbors of the same level before going deeper in the path. So here we selected 2 and 5. We have visited these ones. And then is that we are going to move to the neighbors of both 2 and 5. So let us suppose that we select to visit first the neighbors of 2. We have selected 4, 3, and 6. For the case of 5, we see that there are no neighbors, so we can continue through the neighbors of 2. So in the neighbors of 2, we had 3, 4, and 6. So you see that the case of 4, for the case of 3, there is one neighbor that has not been visited, which is 7th. So in the tier pass, we will visit that tier level, so that node number 7th. And then we are going to check the other nodes, 4 and 6. So, but if we go to those other nodes, we see that all of its neighbors have been visited. So the idea then is that we are moving back, and you see that we have visited actually all the nodes. So this was a quick introduction to both algorithms, Deep-First Search and Breadth-First Search. So in this part, we conclude this very short tutorial, this very short introduction, this part about graphs, so definition and examples, the representation in the computers, about the two search algorithms. In the next part of this talk, we are going a bit deeper, and we are going to look how we can implement as an exercise, a graph in C++ and how we can create an algorithm for visiting the nodes, just as we did here with DFS and BFS.